There we go. All right, so today we are finishing up our review of statics and just going to look at the final couple of concepts. And also, homework one has been posted on Brightspace. You have to go and look for it under assignments. All right. If you can't find it, let me know and we'll figure it out. But it's under assignments. All right. And also, the first review session, the tutorial session, sorry, is going to be tomorrow. So you guys can attend that if you want to, think of it as a study session where you can go get your questions answered, or also just start doing the homework. All right. Okay. So today, the first thing that we're going to look at is centroids. All right. So let's say that we have our X and Y axes, standard stuff. X, Y. And let's say that there is some plate that's on there, which has the dimension such that, defining the dimensions in terms of the coordinate system, say it's B in the X direction and it's H in the Y direction, right? So now we want to find the location of the centroid, which is where the center where the center of the mass acts from, right? So the way we do that is you take a really, really small area, technically infinitesimally small, right? Thanks to the ideas of Isaac Newton. Then we can say that the area of this really small part is equal to the x dimension, which is dx, times the y dimension, which is dy, right? And the definition of the centroid, the location of the centroid, first of all, whenever you're finding a centroid, you always have to have a frame of reference so that you know relative to which point you're finding it out, right? Here, we drew the coordinate system, which is at the corner of the plate, right? So the definition is, and this is the symbol that's used for it. So for the x coordinate, you're basically integrating over the whole area with respect to the location of each of these areas, right? So let's say that that's x, and that's going to be y. And then you do it such that you do it over the whole area so that you cover the whole area. And then this is just simply divided by whatever your whole area is going to be. And then similarly for the y, you do the same thing, but now you're finding out in terms of the y coordinate, all right? So there you go. So it's basically you're integrating the location times the area, integrating that, and then dividing basically over the whole area. So for this specific example that we set off with this rectangular plate, which has dimension b and h, right? Let's find out what the denominators are first. So we have the denominators being the total area, which is the same for both of these, right? So you have A is equal to area times the integral over the whole area times dA. And dA is nothing but a double integral, right? You integrate in the x direction and you integrate in the y direction. So the way that you write that out is 0, h, 0, b. And then dA, we know, is just equal to dx times dy. Right? And the way to do this is, you integrate your x first, then you integrate your y first, right? You guys are super familiar with this. So integrating the x first, you get dx, the integral becomes x, and that is going from 0 to b, right? So that becomes equal to h, that's b minus 0 dy, right? That is equal to b times y times 0h is equal to b times h minus 0. That is equal to bh. All right. So that is your area, which makes sense, right? Rectangle plate, area is just going to be b times h. We just proved it. Thanks, integration. And then we go on to find out the numerators, right? So for your x, dA, again, the area becomes a double integral, 0 to h, 0 to b. Now you have x times the dA is the same thing as before, dx times dy, right? Now, what is the integral of x dx?
X squared over 2.
X squared over 2. So this becomes x squared over 2. Now you're going to 0 to b, dy. Pull that half outside, 0 to h. You end up with b squared minus 0 times dy. And that ends up being equal to 1/2 of, so dy 0 to h is just going to be h, right? So you end up with half b squared h, right? So let's call this expression the equation number 2. Similarly, you do it for y dA. I'm not going to write the whole process out. You guys are super familiar. You end up with half times b times h squared, right? So let's say that is expression number 3, right? So from the expressions 1 and 2, which is 1 is for the area and then 2 is for the x, you see that the location of your centroid for the x location is just equal to half times b squared h divided by bh, right? So h cancels out, b cancels out, so you get half b, right? And then similarly, you get that y is equal to half times h squared b over bh. So there h cancels out, b cancels out, so you're left with h over 2, right? So this is basically the general process of how you find out the centroid. And we did it for a simple rectangular area. Now in your homework, you have to do it for a slightly different shape, as you'll see. And you'll actually have to go and do the integration, right? Again, you're expected to understand how integration works and what happens, but to make your life easy and spend less time doing the math and more time just setting up the problem, I have also posted a Mathematica notebook, which shows you how to do integration and differentiation. Let me show that to you guys real quick. So if you go to the folder Mathematica Notebooks, you'll see a new notebook there called Mathematica Tools for Dynamics. And there you'll find an example of integration and you'll find an example of differentiation as well. So feel free to use that to do your problems when you're doing them for your homework. All right. Next thing we're looking at is the area moments of inertia. All right, and we're going back to the general XY coordinate system. I'm not going to draw it out. So you have the moment of inertia about the x-axis. Ix is equal to, the definition again is such that now you're integrating y squared over your entire area, right? So let's say this guy, let's call it, number it, expression number 4, right? what is the important thing to note here is that when you're finding the moment about the x-axis, right, you're using y and not x in the integral. All right. Similarly, then you have moment of inertia about the y-axis, right? You have Iy is equal to x squared times dA, right? Let's call that expression number 5, right? And what are the units, right? So the units of the moment of inertia are length to the power 4, right? So I lied, we're obviously going to draw it out. So you have x, y, right? And then you have some random body over there, taking your infinitesimally small area inside. Let's say that's dA, right? And it's in, you're doing it in terms of some location, right? So about the x-axis, the way that typically you go about writing it out is, you draw those two arrows like that. So that's your moment of inertia about the x-axis is like that, referred to, then you can say that that's for your y, right? And then similarly, you have your x and you have your y position, right? Then you also have what's known as the polar moment of inertia, which is basically, right? So if you draw a straight line from the origin directly to the point, right? So now you're going into your polar coordinates, right? And the way that that's defined is that you define this angle theta, and then this length from the origin is equal to r, right? And you have this direction, the unit vector in this direction is referred to as ER. And then you have the perpendicular direction, which is called E subscript theta, right? And that is 90 degrees. And then it's about this axis here that you have what's called that polar moment of inertia, right? So let's draw it out in black like that. And we refer to it as J naught, right? So you have the polar moment of inertia. J naught is equal to, the way that that's defined is that now you're looking at this dimension r, right? So you're integrating r squared times dA, right? But r squared can also be written as what, right? This length is equal to x, right? And that length is equal to y. So what's r squared in terms of x and y?
X squared plus y squared.
X squared plus y squared. Thank you, Mr. Pythagoras. Mr. Pythagoras or doctor? I guess they didn't have PhDs back in the day, right? So let's go with Mr. Or this contributions were so good, maybe Mr. Doctor, Mr. Dr. Pythagoras. All right, J naught is therefore, what does this mean there, right? This means that this is equal to the integration of x squared dA plus the integration of y squared dA, right? You spread it out. And what does that mean? This guy is what? Iy, and that guy is what? Ix. So basically, J naught is also equal to your moment of inertia about x plus the moment of inertia about y, right? Let's refer to that as expression number 6. And then sometimes another useful thing is called the product of inertia. That is defined as I, and different people you use it differently. I've said x, ix, and iy here. Sometimes you might see people, say xx like that. They mean the same thing, right? I'm just shortening this out to make our lives easy. All right, so I subscript xy, and that is just an integral of x times y going for dA, right? So that is expression number 7. And an important thing when you're looking at rotation and these moments of inertia is this thing called the radius of gyration. And this is a bit of a personal accomplishment for me over this winter. I officially learned how to hula hoop. Been trying to do it wrong all my life, and I did it. And it was basically just had to keep the hula hoop up higher, closer to my chest. It was pretty easy to do it. But yeah, so now I can gyrate pretty well. All right, so we have the radius of gyration, and that the symbol I refer to that is k, right? And that the definition is that it is the distance at which the entire area would need to be located at to give the same moment of inertia as the actual area. What does this mean? Just a bunch of words. Never fear not, math makes life easy. Ix is equal to a times y squared dA, right? So we're just going to assume that this is a constant now, right? So this is going to equal a kx squared dA. So you can just pull the constant out. You get kx squared times a dA. So that is just equal to kx squared times the area, right? So it's basically you're taking the integral out of it and then finding out what the constant would be when you take that integral out of it, right? So the way that it's defined is that the radius of gyration, 3 dots, this is my therefore symbol, kx is just equal to whatever the moment of inertia that you found is divided by a, and you take the square root of that, right? And that is, let's call that expression number 8. From this expression here, right, what are the units of the radius of gyration going to be?
Length.
Length, right? Because the moment of inertia is length to the 4. A is length squared. Length 4 divided by length squared, you get length squared. Take a square root of that, you get length, right? So just length like that, right? All right, so that's the radius of gyration. Very important thing. Next is called the parallel axis theorem. All right, and this is important, right? Because typically when you go and look, you'll be given the classic moments of inertia about the standard axes, about the centroids and things like that, but you always have to find out the moments of inertia which is not going to be about those axes. And in order to do that, you use the parallel axis theorem, right? So let's get the hard definition out of the way. So moment of inertia of a body about any axis is equal to the moment of inertia of the body about the parallel axis through the centroid of the body plus the area times the distance squared between the axes. So between the axes that's passing through the centroid and the axis that you're trying to find the moment of inertia about. All right, and we don't have the time to go through the derivation for this, but I'm sure you guys did when you were looking at statics, right? So when we say prime, that is what we're saying is the moment of inertia about centroid, right? So whenever we see the symbol prime, so A D squared, right? So let's say that's expression number 9, right? It's a diagram. What does that mean, right? So let's say you have some area like that, right? Then you've got some coordinate system that you define, right? Which is the origin of which is not at the centroid, right? It's just like that over there. What you need to do is to find out where the centroid is in location to this frame of reference that you've drawn, right? That's the first step. Then when you find it out, you move your coordinate frame there, and that's what we say is x prime, y prime, right? So typically when you see in statics and dynamics, see x prime and y prime, that means that your coordinate system is passing through the centroid, right? So let's say that this is a centroid C, like that, right? And then what is the task at hand? The task at hand is to find the moment of inertia about some random axis, right? So let's say, sorry about that, Seamus, easy, take it easy. Another perk of teaching from home, you guys get to hear Seamus in the background. So, and this axis is parallel about these x-axis over there, right? So this symbol here means parallel, right? So you guys know that about this one, about the axis passing through the centroid, we said that the moment of inertia is ix prime, right? Then the perpendicular distance is what you're interested in, right? Like that, and let's say that that distance is d, right? So basically, the moment of inertia about this axis, which would be your IL, is equal to the moment of inertia about the axis, the parallel axis that passes through the centroid, times the area times this perpendicular distance squared. All right? Good stuff. Last, I think this is the last one that we're going to look at today. Yep. Impending motion. Right, so we've got, let's say you've got some body which is on a surface and you have some force P that is acting on it, right? And there is friction here, so friction exists. Right, so what does the behavior of this friction look like, right? So if we draw the free body diagram out, let's say that we have our frame of reference, x, y, then we resolve our P, right? So you'll have a Py and you'll have a Px, right? What other forces will we have? Again, we're on Earth, right? So the regular stuff, you'll have the weight going downwards. What else? What am I missing?
Normal force.
Normal force. What else? Friction. Right? So friction is going to oppose your motion because this force P is going to want to move it in the positive x direction. So your friction force opposes the motion. It's going to act in the opposite direction, right? So as this force P is increasing, right, what does your friction force look like, right? So if you plot your friction force as a function of Px increasing from 0 to some value, right? What do you see? You see that the friction force increases directly as P is increasing, right? So you have Px here, you have F here. How would you express F as a function of Px? Like, what is this? What is the equation of this line?
F equals px.
F equals Px, right? Whatever the Px is, F is going to be equal to that, such that there is no motion that takes place. Then you go up to a certain value, right? Like that over there, right? And that is the point at which you say you have impending motion. Right? Because you will have your three expressions, right? You will have your equilibrium forces in the two directions and your moment equilibrium. So three equations. And then you will have this F max value, which is equal to what?
Coefficient of static friction times
Normal force,
normal.
right? So that's the value over there. Then if P keeps increasing, what happens? Beyond this point, if P increases, what happens?
Friction will decline.
Friction will decline, right? And then it'll stay constant, right? And this is the stuff that we are going to be interested in a couple of weeks from now, because that is where dynamic motion comes in, right? And here, what is the value of friction here?
Kinetic coefficient.
Kinetic.
Oh,
There you go. Coefficient of kinetic friction times the normal force. All right, good stuff. So the kind of problems that you see right? So you don't know when you're dealing with these friction problems where you are, where you are along this curve, right? You don't know if there is, if you're in the static part or you're in the kinetic part. So you have to go and solve the problem to figure out where you are, right? So right? So the way you go about it is, or the easier way, there's multiple goats, there's many ways to skin a goat, right? So my suggested way is that you assume static equilibrium, right? Then you solve your equilibrium expressions to find what your friction force should be. And then you also solve for what your max friction force should be, right? And then if this friction force that you solve for is less than or equal to this max, then this assumption of static equilibrium is good. Right, and you have you'll have a homework problem that you need to do to use these steps in, right? All right, so then if you're right at the point of impending motion, right? And you know where you are. Right? You just have 4 expressions, right? You have the 4 expressions for your 3 equilibrium and for your max friction, right? So just solve them. Easy peasy. Right? Then if you know that you're at impending motion, and you don't know where you are, you have to get a bit existential about it, right? You have to ask yourself, what can happen? And then you figure out what is plausible versus what is not, right? So what does that mean? So if we take a look at an example, you've got a big body and you've got a small body, right? Over here, on this surface, you have one coefficient of static friction. Over here, you have another coefficient of static friction, right? And let's say that on this top body, you have a horizontal force, which is pulling it, right? You just have to go and look at your problem, right? So now you need to break it up into your individual free body diagrams. Take P, you have the weight, you have a normal force, right? And then you take the other free body diagram, right? And then, you know, every action has an equal and opposite reaction. So you'll have N1 downwards like that, right? And then you have, well, I forgot to mention the friction force up there, right? So F1 like that, right? And then again, friction, same as normal force, equal and opposite. So you'll have an F1 over there, right? Then you'll have an F2 down here, which is opposing the overall motion. You have that normal force, and then you have its own weight to contend with, right? So you basically have to go and see what can possibly happen, what can happen, you know, and solve it using the first step, right? The important thing to note here, quick note, which you guys are very familiar with, but just to point it out, that this N1 is not W1, right? You need to solve for N1 and then plug that in there. It's not a simple transfer of weight. So this is all the stuff where there is no movement. For everything else, you guys are in the class to learn it. So the rest of the cases are dynamics problems, which we will become very familiar with when we look at the kinetics in a couple of weeks. Right? Lovely. So that was the theory part. Let me switch gears here.